Welcome back to Bio 6612. Today we're going to talk about predictive power and logistic regression and how to compare different prediction metrics. So for most regression modeling or statistics in general, there's this idea of estimation versus prediction, which are two possible different goals. When we're focused on estimation, we are interested in the expected value of the outcome for given values of the explanatory variable. And generally, we want a parsimonious model, a model with not too many predictors, something simple that fully explains the relationship between the predictors and the response. And when prediction is our main goal, we want to predict the value of the outcome for given values of the variables. And we don't necessarily care as much about some parsimony and interpretability. Basically, we want to focus on being able to predict values for a specific individual based on their covariates. So when the main interest of a logistic regression in particular is prediction, how well can we predict the outcome based on the values of the covariates? And in general, I just want to highlight that predictive power is different from model goodness of fit. Even though in some examples I'm going to calculate both goodness of fit statistics and predictive power measures in this lecture. But a model can have good prediction but poor fit, or vice versa. And so measures of predictive power fall into two camps. One are measures based on the log likelihood, and these are basically different versions of R-squared for logistic regression called generalized R-squared or the max rescaled R-squared. And then there are also measures based on predicted probabilities and observed responses. So basically, how well do your predicted probabilities relate to or agree with the actually observed Y values? And these measures are Summers D, gamma tau, gamma, Kendall's tau, and the C index, which is also called the AUC. And there are other measures, but these are the ones that I'm going to focus on. So the predicted power measures based on the log likelihood are listed here. The generalized R-squared is calculated as 1 minus the ratio of the log likelihood under the intercept only model divided by the log likelihood under the model of interest raised to the 2n. And in this case, n is the sample size. And this is also called the Cox and Snell R-squared, and it has an upper bound of less than 1. Which isn't always as intuitive as you would think, because at least in R-squared from linear regression, you would expect the values of R-squared to be between 0 and 1. And so the max rescaled R-squared value is very similar to the generalized R-squared, except it divides R-squared by its upper bound, so you now have your value is greater than or equal to 1. So it has that sort of more intuitive interpretation. However, in general, these should not be interpreted as a proportion of variance explained by the covariates as in R-squared, because it's a little bit more complicated than that. So actually, these predictive power measures based on predictive probabilities are a little bit more popular for the most part. And these measures use information based on the number of pairs of observations in which one observation had the response and the other did not. So if you have yi's that can be 0 or 1, you compare all of the 1s to all of the 0s. And then you take some definitions based on that. So for example, let's say you have two subjects, the ith subject and the jth subject. And for subject yi, they have a response value of 1 and a predicted probability based on their logistic regression and the covariates of pi hat I. And for yj, they have a response of 0 and a predicted probability based on their covariate set of pi hat j. So that pair is called concordant if the observation with the response, yi, has a higher predicted probability than the observation without the response, yj. So otherwise, you can write that as if yi is greater than yj, then the pair is concordant if pi hat I is greater than pi hat j. And discordant is the opposite. So with discordant pairs, if yi is greater than yj, but pi hat I is less than pi hat j, we would say the pair is discordant. And if both observations have the same predicted probability, it's considered a tie. So there are a couple of measures that use these definitions to calculate sort of predictive performance. And so let C equals the number of concordant pairs from the last slide, and D equals the number of discordant pairs. And so each of these measures, summer C, gamma, tau A, and the C index all calculate some number based on those number of discordant and concordant pairs, along with N, which is the total number of pairs, including those with the same responses, say like both have yi, both have both have y0 or both have y1, and T is the number of ties. And for all of these measures, larger is better. So larger means better predictive power. And finally, this isn't exactly a predictive measure, but it's good to understand the idea of confusion matrix to help you determine where your model might be predicting poorly. And confusion matrix is a common diagnostic tool for classification or binary prediction problems in general. It's used a lot in machine learning. And it's also called a classification table. So let's say you do a logistic regression, and you want to get, and you have the true value of y I equals 1, and your pi hat yi equals 0.7. Often what you would do is you would use that pi hat to calculate a y hat I by drawing some threshold value at all the pi's. Say if pi hat is greater than or equal to 0.5, then y hat equals 1. Otherwise, y hat equals 0. That's how you get predicted values for y hat. So in this case, if you use that rule, we would say that y hat is equal to 1 as well. So they'd be the actual observation and the predicted value would be in agreement. You don't have to say that pi hat equals 0.5 is the cutoff. It's just the most popular. And so, but once you determine some cutoff, you can classify your y hat value. You can get your y hat values. You can get a predicted 0 or 1 for each observation. And then you can determine how closely those predicted y values relate to the observed y values. This is also called how many false positives, false negatives, true positives, and true negatives are predicted by your model. And you just look at, and what you do is you just make a little table that says, okay, how many true positives did I calculate? That's the number of observed ones that also predicted to be 1. False positives, the observed zeros that were predicted to be 1. False negatives, the observed ones that predicted to be 0. And true negatives, the observed zeros that were predicted to be 0. And this can help you say, okay, well, if we're getting a whole bunch of false negatives, maybe we have to determine why our model thinks that our observations are zeros when they actually should be 1, for example. You also want to spend a little bit more time talking about the area under the receiver operating curve, also called just the AOC, because this is a very common diagnostic tool in regression model and logistic regression and in other predictive classification problems. So the ROC curve is just a plot of sensitivity versus 1 minus specificity, where sensitivity is the true positive rate and specificity is the true negative rate. And here with the AOC curve, the goal is to choose a threshold for pi hat, a threshold that allows you to predict the 0, 1 values of y that will maximize sensitivity and minimize the 1 minus specificity. And it's also helpful for visualizing how well a predictive model can distinguish between true positives and negatives. Then the AUC is actually based on this ROC curve and is itself a measure of predictive power that is equivalent to the C index. And what this means intuitively is the further the curve is from the diagonal line, which means basically a coin flip, no predictive power, the better the model is at discriminating between the positives and the negatives in general. So for each of these measures, I'm going to go through an example with weight loss attrition. So we have a weight loss program, and researchers are interested in attrition, basically whether or not people drop out of the program. And the question in particular is baseline BMI or baseline physical activity a better predictor of attrition? And the variables in the data are complete. This is the outcome variable, which is equal to 1 if the user completed the weight loss program or 0 if the user dropped out. Another is gender. We also have age and years, BMI, which is a continuous covariate, and steps, which is also continuous, which is an indicator of the baseline physical activity in number of steps per day. This study has a small sample size, n is equal to 20. So we would say that for inference, the LRT is more appropriate than the WALD test, the likelihood ratio test, that is. Though I'm not going to talk about that more, I just wanted to point it out. So this is coded as 1 equals completion, so completing the study, and 0 equals dropout. But since we're actually interested in dropout for this particular application rather than completion, we reverse the order of the outcome. So first I load in the data set. This is a .txt file, which will be available to you on Canvas. And then I use a mutate statement and a factor statement to factor this variable so that the first level is 1, which is completed, and the second level is 0, which is dropout. So now in a logistic regression model, 1, the completion will be the reference variable category, and the dropout will be the main category. That will help with interpretation for the model. And so the first model that we're interested in, which I'm going to call model 1, is the model that includes only steps as a covariate in our logistic regression model. And so we can run that model here and look at the coefficients. And we get a pretty small estimate for steps, but that's because this relates to only like 1 step per day increase. What I mean is you can take a lot of steps, so if you only have 1 more step, it's not going to increase your odds ratio by a lot. One thing that we could do is look at like steps times 1,000 to get this at a different scale. That might be a little bit more easy to interpret, but that's just something I think, and the results would be the same in terms of the p-value and the significance of the covariate, but just something to think about. And this covariate has a significant p-value as well, though we could also look at the likelihood ratio test. And so for this model, I'm going to go through and I'm going to calculate all of the different measures of interest that we discussed in the previous couple slides. So just in case you aren't aware, the syntax name of package and then colon, name of function allows you to use a particular function even if you haven't already loaded that the clean names function from the janitor package. I could use just load library. At the beginning of the document like I normally do. And then I could just say, okay, clean names for my data set. Or what I could do is I could just, and that loads all of the functions from the janitor package, but we're only using this one. So another thing I could do is I could say janitor clean names, name of data set. And those are just two different ways to load functions in R. If I'm going to use a lot of functions from a package, I'll usually use a library statement. If I'm only going to use one function from that package, then I'll use the janitor statement. And the reason not to load all of the names, all of the functions, if you don't need all of them, is sometimes the same packages have the same name. Different packages have the same names for different functions. And so if you load both packages, it'll be in conflict and you won't necessarily know if you're calling the right name of the function that you want. So in this code below, I define a function that calculates predictive measures for logistic regression. And for each of the measures that I'm calculating, I'm calling the name of, I'm using this syntax to just to show you that here's the name of the package and here's the name of the function. Because I want, even though I already loaded these packages at the beginning of the document, I just want you to be able to see which functions are coming from which package, so you could also calculate these yourself. So I define this function that is called get predictive measures, and it has two arguments. One is a model of interest, that's your logistic regression model that you've calculated, and the other is model name, and this is just whatever you want to call the model. And I'll show you why that matters later. But what this model does is, okay, so first I'm going to calculate R squared values using this R companion package and the Nagle-Kirk function, which gets your scaled R squared value and your generalized R squared value. And then I'm going to create a table that has all of these different measures in it. First, it's a model name that just lets you know what model you're working with. I'm going to calculate the AIC and the BIC. I'm going to calculate the Hosmer-Lemeshow statistic and the P, and actually retain the p-value, where that was a thing for goodness of fit from a few lectures ago, where a large p-value indicates a good fit. I'm also going to calculate the generalized R squared, the rescaled or Nagle-Kirk R squared, the Summers D, the gamma, the tau, and the C index. And so when I run this function, I am going to return a table that has all of these different measures of interest. So below, we can call that function that's defined in the previous slide to get those measures of predicted power. So I'm going to call those measures and I'm going to call that function. I'm going to use model 1 as the model of interest. I'm going to just call it model 1. So in the table that's returned, we know that the measures are coming from model 1. And I'm going to store all those values in a variable name called model 1 measures. And if I just print that out, you can see, okay, I have just a table with one row where the model is called model 1, and you have AIC, BIC, and all of these other statistics that I've calculated. And most of these statistics are not going to be something we can outright use to determine goodness, though larger values generally do mean better prediction. But we're going to be able to compare those to other models that we run. But one thing that you can notice is the Hosmer-Lemeshow statistic is 0.6, which is a great deal bigger than 0.05. So if you were doing a goodness of fit test, you would say that this model fits the data. So this plot shows predicted probabilities from Model 1. And so for all the different values of number of steps per day that you can take, these are the predicted probabilities, the pi hat values, which is the probability of dropping out. And then I also colored this by your actually observed probability, where blue indicates that you dropped out, and red indicates that you did not. And you can see here that in general, the fewer steps that you have, the higher probability of dropping out. The more steps you have, the lower your probability of dropping out. And then you can also see that in general, there's good separation between probability of dropping out and actually dropping out. So if you have a high probability of dropping out, then you were more likely to have actually dropped out, which is an indication that the model is doing a good job of predicting. If you're going to draw some threshold, if you drew a threshold at 0.5 here, then this person would be misclassified. So what you might want to do for this model instead is actually draw a threshold of maybe 0.75 to correctly classify that individual. And then you can also see there's one guy in here who has just over 6,000 steps and had a predicted probability of dropping out that was pretty low, but they actually did drop out. So that was another person that would be misclassified by your model. So we're going to also look at another model, because we're interested in this question of whether BMI or steps are a better predictor of completion. And in the second model of interest, we're only including BMI as a predictor. So we're going to run that model. We're going to call it Model 2. You can calculate coefficients. The p-value for BMI is still significant. And we're going to once again use that get predictive measures function that we defined to plug in Model 2 as the model of interest and calculate those predictive measures. And here we get a set of another values that are also rather high, though lower than what we calculated for Model 1. And also you can see that your Hosmer-Lemeshow p-value is now less than 0.05, which is potential evidence that we don't have a good fit for this model, that the model doesn't fit the data. So I also plotted the predicted probabilities for this model. And here you can see that having a low BMI indicates a low probability of dropping out, and having a higher BMI indicates a higher probability of dropping out. And you might think about if you drew the threshold at 0.5 here to decide y hat, then this person who completed the study would be misclassified as having dropped out. So instead, in practice, you might want to draw the threshold here. Similarly, we have another, you can't really see this too well, but there's a little blue dot in there. So that's one person who would have been misclassified as completing the study, but actually dropped out. So we want to use these metrics to compare between the two models. And the conclusion is, after looking at these, that Model 1 is the winner. Basically, across all measures, when trying to predict odds of attrition, we prefer Model 1, the model with steps, over Model 2, the model with BMI as a predictor. And AIC and BIC are not model prediction characteristics. They're ones for model selection. but I still have included them because we learned about them recently. And for these, we would select model 1 because the AIC and the BIC are lower. Again, the Hosmer-Lemma test is a goodness of fit statistic. That's not for predictive measures, but I'm including it anyway. And in this case, we would conclude that model 1 has a good fit to the data, but model 2 does not. But you wouldn't directly compare the Hosmer-Lemma test for each of these models. The p-value would just compare it to some threshold like 0.05 to see whether or not the model is a good fit for the data. But it could have been and in this case, the goodness of fit test agrees with the predictive measures, but that's not always going to be the case. And then the rest of the predictive probabilities for all of these values here, higher is better. And that's, you can see across all of these measures, model 1 has better predictive power than model 2. And so I said I want to calculate some confusion matrices. And here I'm using a function called confusion matrix from the Caret package, which is a nice package for tools related to machine learning that I actually use quite a bit. And here I'm using 0.05 as the cutoff to decide whether y hat is 1 or 0. And then I'm just making a table where you can see, okay, this is the true negatives, those who are 0 or who are correctly predicted as 0, and the true positives, those who have an observed value of 0, of 1 and correctly predicted as 1. And you also have your false negatives here and your false positives here in the way that this table is set up. And you can see for the first model, we do a pretty good job, except there's one false positive and one false negative. And in the second model, we also have one false positive and one false negative based on this 0.5 cutoff. So based on the confusion matrix alone, they have similar accuracy rates. And we can use that confusion matrix to calculate these the ROC curves for model 1 and model 2. And for these curves, we have sensitivity on the y-axis and specificity on the x-axis, and we're looking for a curve that is far away from this diagonal line that I just drew, which would indicate no way to differentiate between true and false positives and negatives. And the AUC is going to be the value in here. And here you can see that basically we want to maximize the area over here, because that gives you, find the points that have both high sensitivity and high specificity. And you can use these curves to help determine what is the optimal cutoff for pi hat to define your y hats.